we are seeking to solve this equation here. Note that it is different than the previous uh, uh, non-homogeneous differential equation of order n. It's still classified as being linear, but before, when we talked about this very large nth order differential equation, we would say that we had some coefficients a sub n and then a sub n minus 1 and so on to a sub 1 and a sub naught. But we never talked about it in terms of some other variable like x to the n associated with each derivative. And then here, x to the n minus 1, and then x squared that would go with y double prime, and then x would go with y prime, and then no x term associated with y. So this is called by name the Cauchy Euler equation, and the reason why is that Augustin Cauchy and Leonardo Euler both solved this differential equation at different times, where each one did not collaborate or use the other's information. So in some circles it's called Cauchy equation, some Euler, but we put them together. And we had to because Euler has other equations and formulas out there, and so does Cauchy. But at any rate, how do we solve this? It's very similar to how we solved before using the method of solving nth order differential equation with constant coefficients. But here, my coefficients are not constants. The a, the b, and the c for equation 1 would be constants, but the x squared, the x, and those type of variables are not constants. They are variables. And so we want to try to determine how do we solve this. And so what I want to show you, because most of what we'll do today would be at the second order, right, the second derivative type of differential equation. So there, if we let n equal to 2, and then we'll write a sub 2 as being just a, and then a sub 1 as being this b here, and then the a naught would be c, constants. Letters are constants, and so you can represent them with any type of letter you want. Well, to understand this, let n equal to 1. Let n equal to 1, and see how the solution looks. If you get an idea of that solution from n equal to 1, then you can extrapolate that the solutions for n equal to 2 would be similar, n equal to 3, and then so on would have similar type form. So if we let n equal to 1, no red. This gives us really just this part here, bx dy over dx plus cy is equal to 0. I'm going to let this b and c, since we're talking about b and c, let's just talk about a and b, if you will. So that is ax dy over dx plus by is equal to 0. I can solve this by separating the variables. So if I multiply through by the dx and subtract this by on both sides, do that at the same time. This is ax times dy is equal to negative by dx. Again, trying to separate the variables to get the like terms together. We divide y on both sides, divide ax on both sides. So we have 1 over y dy is equal to negative b over a times 1 over x dx. That negative b over a, if you will, let's just write it as something else. Let m represent negative b over a. So this implies that we have 1 over y dy is equal to m times 1 over x dx. The variables are separable, so we integrate. And so that gives us the natural log, the absolute value of y is equal to m times the natural log of the absolute value of x plus some constant, let's call it c sub 1. If you exponentiate both sides, this gives us e to the natural log of the absolute value of y is equal to e to the natural log of x to the m times some e to the c sub 1. Well, that gives us just y is equal to e to the c sub 1, let that equal to c, times here, e to the natural log of x to the m is just x to the m. So that here, just for educational emphasis, let c equal to 1. This implies that y is equal to x to the m. So my solutions for the Cauchy Euler equation will be of the type x to the m, not e to the mx like we saw back in chapter 4, section 3 and section 4. And the reason why they're different is because I have associated with each derivative an x to some nth term. Right? So that's what changes the solutions dramatically. So thus x equal to x, while y equal to x to the m is a solution of a differential equation where m is a solution of some auxiliary equation. Well, why is that? Well, if you let y equal to x to the m, y prime is equal to m times x to the m minus 1, and y double prime is equal to m times m minus 1 times x to the m minus 2. We want to solve this problem. We want to solve ax squared times y double prime plus bx times y prime plus c times y equal to 0. That's our goal for today, to solve this. And then you can change the 0 to some other function, g of x, and you get a non-homogeneous differential equation. So our goal is to solve that. So I'm going to replace the y double prime with m times m minus 1 times x to the m minus 2. Replace the y prime with m times x to the m minus 1. Replace the y with x to the m. So here, doing that, this ax squared y double prime plus bx times y prime plus cy is equal to ax squared, well, y double prime here is m times m minus 1 times x to the m minus 2 then plus bx times y prime, that's m times x to the m minus 1 plus c times y, and y is x to the m. We simplify that. To simplify, notice that x squared times x to the m times x to the negative 2 would cancel out the x to the negative 2 with this x squared. This x to the first would cancel out with this x to the negative 1. So what I have is, and we're just going to factor out x to the m. At the same time, I have left a times m minus 1 plus b times m plus c. This is equal to 0. Well, if the solution is said to be on the interval from 0 to positive infinity, then x to the m cannot equal to 0. So that means what's in the bracket has to be equal to 0. So this implies that this a times m minus 1 plus b times m plus c is equal to 0. You can simplify that. This is a m squared minus am plus bm plus c is equal to 0. Or you can write it like this. This is a m squared plus parentheses b minus a times m plus c is equal to 0. What does that look like? A quadratic equation, right? Of which here, this quadratic equation has 3 possible solution types. Very similar, our skeleton model would be before. We talked about distinct roots, talked about repeated roots, talked about complex roots. We use the same argument, but the solutions look a little bit different because we have these x to the m terms instead of e to the mx terms. Right? I don't know if you remember back in chapter 1 where they had a couple of problems, and they were these problems, and said that assume that the solution is of the type y equal to x to the m, and then see if you can kind of map that through the particular equation to be able to solve for, at that time, it was really the auxiliary equation. And we had one problem that said, assume that the solution type is y equal to e to the mx, solve for y prime, solve for y double prime, map that through the equation. That was back in chapter 1. And I told you that we're setting everything up for what's to come. So we're talking about here what has already come, right? So there are 3 solution types to this. Equation 3 has 3 solution types. Distinct, repeated, and complex roots for m, right? Equation 3 is called the auxiliary equation for the Cauchy Euler equation. One L, excuse me. All right, so here's the first case. Yes, sir.
Are you going to want us to be able to derive this on the prime?
It's possible. It's possible. It's possible. If you have distinct roots, that is that you have different m's, m sub 1 and m sub 2, then the solution is written as y sub 1 is x to the m sub 1, and y sub 2 is x to the m sub 2. So we write the solution in this form right here. So let's see. Here's how we solve. You let y equal to x to the m. Y prime is m times x to the m minus 1. The proof that I just did, the problems just mimic the proof all over again. And then here, y double prime is equal to m times m minus 1 times x to the m minus 2. So I look at the equation. This is x squared times y double prime minus 2y here is equal to 0, but let's just write what it is. This is x squared. Y double prime is m times m minus 1 times x to the m minus 2. Then this is minus 2y, but y is x to the m. That's equal to 0. Now notice here that x squared, I guess I can just write it out just so you can see. This is x squared times m minus 1 times x to the m times x times to the negative 2 minus 2 times x to the m. You see that the x squared and the x to the negative 2's, they cancel out. So this is, you can factor out x to the m. You have left m times m minus 1 minus 2. M times m minus 1 minus 2, that's equal to 0. So this has to imply then that m times m minus 1 minus 2 is equal to 0. Simplify that. This implies that this is m squared minus m minus 2 equal to 0. And lo and behold, we get right back down to factoring. So this is m minus 2 times m plus 1 equal to 0. That implies that m is equal to 2 and m is equal to negative 1. So my solution, the complementary solution, is y sub c is equal to c sub 1 times x to the second power plus c sub 2 times x to the negative first power. Thought I put that emphasis. You know, I had teachers like that. Boy, they used to wake you up, you know. Now again, you see how the solution is written in that form there. Right? Now let me give you the shortcut, and sometimes I'm not going to write it because if I write it, I don't know, somehow it throws people off. If there's a y prime, you just write an m. If it's a y double prime, replace that with m times parentheses m minus 1. Right? If it's just a y there, you don't write anything. Just if it's 2 times y or 1 times y, you just say 1. Or if it's 2 times y, you just say 2. Let me show you with this problem. That's the shortcut. You're welcome to use it. See this problem right here? This guy is is y double prime. I'm going to write m times m minus 1. M would represent a first derivative. M minus 1, that's the second derivative combined. Minus 2 equal to 0. Isn't that what we had down here? M times m minus 1 minus 2 equal to 0. That's the shortcut. Yes, sir. If it's Cauchy Euler. I'm solving a Cauchy Euler differential equation. Look at this problem right here. This is going to be simply 4 times, is y double prime, so it's m times m minus 1 plus, here if it's y, just write 1 plus 1 equal to 0. All right. So this is 4m squared minus 4m plus 1 equal to 0. You can factor 2m minus 1 2m minus 1 equal to 0. So this implies that we get m equal to 1/2 and m equals to 1/2. That's a repeat. Right? That's a repeating root. But you see how quick it is to do that shortcut? And if you got that, you can use that. If that gets you mixed up, then just go through and just say let y equal to x to the m, and then y prime is m times x to the m minus 1, and then y double prime is m times m minus 1 times x to the m minus 2, and then just go through the steps. I've seen people take the shortcut, and because they were not so familiar with it, then they had not so good results.
So we could like pay for any of the Khan Academy.
No, I just made it up, you know. Well, a few years ago, but I'm just saying it's just, you know, a shortcut. So here, this guy, the answer is y sub c is equal to c sub 1 times x to the 1/2 plus c sub 2 times what? X to the 1/2 times what? Natural log of x, if you watch the video. Thank you, Cameron. What did you say, JC? You didn't call him a jerk, did you? Okay. Just joking. Just teasing, just wake you up. Wise guy, that's the phrase. Wise guy, eh? You know? Why is that natural log of x combined there? If you have repeated roots, the general solution is of this form. C sub 1 times x to the m plus c sub 2 times x to the m times the natural log of x. Why is that? Okay, y sub 2 is said to be the first solution, which is x to the m, times the integral of e to the negative integral of p of x dx all over the first solution squared. Have you seen that formula before? Right. That formula says if I know one solution, I can solve for the second solution using that formula. Right. Well, all we need really is p of x. What is p of x? Well, it comes from this equation, a x squared times y double prime plus bx times y prime plus c times y is equal to 0. This implies that y double prime plus b over ax times y prime plus c over ax squared times y is equal to 0. Why do we write the equation like this? Yes, to determine p of x. Because, look, it's of the form y double prime plus p of x times y prime plus q of x times y is equal to 0. So here we can identify p of x because that's needed for this formula. P of x is b over ax. So y sub 2 is x to the m times the integral of e to the negative integral. P of x is b over ax dx, and this is all over x to the 2m dx. So we integrate up there, so we get x to the m times the integral of e to the negative b over a times the natural log of x That's all over x to the 2m dx. Now, this e to this negative b over a natural log of x can be simplified if I wrote negative b over a as the exponent of x. So this becomes x to the m times the integral of e to the natural log of x to the negative b over a all over x to the 2m dx. So this is x to the m times the integral of x to the negative b over a all over x to the 2m dx. That's an a. Well, since x and x are the same base, then I can deal with the exponents there. So y sub 2 is x to the m times the integral of x to the negative b over a minus 2m dx. But what is m? M is b over a. How do you know that? Okay, remember the equation that m comes from is this. A m squared plus parentheses b minus a times m plus what? Was it plus c? Equal to 0? If you have repeated roots, what does that say about the graph of the parabola? That where that root is, which is the solution, where that root is, what happens to the curve there? Or is there a curve there? Well, yes, there's a curve there. We're talking about a parabola, right? We're talking about a quadratic equation, we're talking about a parabola, right? If you have repeated roots, then that means what in terms of the graph? Both at the same point, indeed. And you can solve it algebraically. I like to use the calculus, the derivative. What's the derivative at that particular point? If you have a parabola, and if it's crescent downward, and you got a vertex at the bottom, or even at the top, right? If it's upside down parabola, what happens at that vertex there for that parabola? The derivative is what? Is equal to 0. You have a horizontal slope, right? If you got a parabola, you got a horizontal slope. If it's like that, the derivative there is a horizontal slope. That means that the derivative is equal to 0. I'm going to use that fact to solve for m. So since we know that for repeated roots, the vertex occurs on on the axis, and, or I should say with, horizontal slope. Parenthetically, the derivative is 0. You know, there's a neat formula for the vertex from algebra that x is equal to like negative b over 2a or something like that. I mean, I never remember that. So I just use the derivative and you always get it. So again, I don't keep anything in my head, but we just keep the basic knowledge. Take this equation, we find the derivative. So here, a m squared plus b minus a times m plus c equal to 0 implies applying the derivative on m. This is 2am plus b minus a is equal to 0. Solve for m. I get m here is equal to, this is minus parentheses b minus a all over 2a. So that becomes minus b minus a becomes a minus b all over 2a. A minus b all over 2a. Will that be the case? Just take that term and replace that for this m up here. So we get y sub 2 is x to the m times, well, it's not an e anymore, x to the, it's negative b over a minus 2 times m. The m here is a minus b over 2a. This is dx. Simplify that. This is x to the m times the integral of x to the, this is minus, not times, negative b over a. The 2's cancel out. This becomes minus a minus b over a. I'm going to just take it all together. This is minus, the 2's cancel. A divided by a is minus 1. Minus this minus is plus. The 2's cancel again. So this guy becomes plus b over a. Well, they cancel. The minus b over a and the b over a cancels out. So I have left y sub 2 is equal to x to the m times the integral of x to the negative 1 dx. Well, that's just the integral of 1 over x. Well, that's just the natural log of x. That's where the natural log of x comes from. X to the m times the natural log of x plus c. Let c equal to 0. And so y sub 2 is x to the m times the natural log of x. If it repeats more than one time, then it becomes, that third solution becomes x to the m times the natural log of x to the second power. Yep. Yes, sir. That's all. Just keep on running that natural log of x up to the powers. The same thing how it happened, you know, back for the repeated roots for the constant coefficients. It was an x term applied, then it was x squared. If it was another one, x to the third, you know, and so on. So the same thing here. Yep. So if you take this guy, this is, if you want to use my shortcut, we can. So this is m times m minus 1 plus m is equal to 0. If it's the first derivative, replace that with m. If it's the second derivative, it's m times m minus 1. Okay. So this becomes, you simplify that, that's m squared is equal to 0. So I have m equal to 0, m equal to 0. So the solution, y sub c, is c sub 1 times x to the 0, if you will, plus c sub 2 times x to the 0 times the natural log of x. Well, x to the 0 is just 1, so just clean that up. Y sub c is equal to c sub 1 plus c sub 2 times the natural log of x. The third case is when you have, well, first we have distinct roots, secondly we have repeated roots, thirdly we have complex roots, where here m is said to be of some form alpha plus or minus beta I. So you expect the solution to look like this, but we have to transform that into solutions that combine cosines and sines. Now, why is that? I think it's just a matter of choice of mathematicians, and just because of time, all of our solutions, whether it's written in, using the Cauchy Euler or solutions that involve summations, using, say, for example, Fourier series, those solutions are all of the types, combinations of cosines and sines. They all, at some point in the initial situation, made use of that Euler's formula to transform this so-called e to the imaginary term I times beta into some cosine beta or theta plus I times sine theta. In my video, I covered how we got this solution. Did you see that? It's very extensive in terms of how it comes about. But in the video, I cover how that is, how that comes about. If you have a question, then I could try to cover it quickly, and then hopefully maybe do one problem. I do know that I can do one problem now and be done, but you need to understand this formula. That's most important. The formula is most important. How it comes about. Well, let's see if I can kind of scale over it just quickly, since you did see the video already, so you got some idea of what's going on. We say that here for complex roots, the solution is of the form y sub c is equal to c sub 1 times x to the, I have to use these roots here, alpha plus beta I plus c sub 2 times x to the alpha minus beta I. And what I'm going to do is just go ahead and factor out what's common. What's common is x to the alpha. So x to the alpha comes out. This is times left. What I have left is c sub 1 times x to the beta I plus c sub 2 times x to the negative beta I. Now I'm going to use Euler's formula to transpose this this equation. Use Euler's formula, that is e to the theta I is equal to cosine theta plus I times sine theta. Hopefully it's something you picked up in trigonometry. Right? The only problem here is that I don't have E. I have X, right? My base is not E, my base is X. That's okay. We're good. So what we'll do here is we're going to translate this X term into a natural base E form by doing this. We'll say here X to the beta I is equal to E to the natural log of beta I. Sorry, man. The 2 slices of bread that I had for breakfast was not enough. This is E to the natural log. This is X raised to the beta I. Good. That makes sense. Because E to the natural log of something is just equal to that something. But that something is X to the beta I. So I write this as E to the, I'm going to bring down the beta I. And I'm going to say that this is I times parentheses beta times the natural log of X. So that is understood to be of the form E to some term times I, which has to be cosine of that term plus the I times sine of that term. Right? Well, I get it. This is cosine. Here the term is beta natural log of X, parentheses beta natural log of X plus I times sine of beta natural log of X. But it seems like I can just finish this and I'll be done for today. I won't have time to work a problem. But the main, if you got a couple of minutes, then the problem is like 2 minutes to solve, you know. I think the main understanding is how we come up with the formula to write the answer. To me, that's what's mind-boggling. I mean, what does that mean? How do we get that? And once you see how you got it, then I think you can with ease work the problem. Yes, sir. How does X to the BI become this? How does this become that? Okay, you remember that you got a principle for the natural log of X raised to some power of M. You can write the exponent M as a multiplier times the natural log. That's what I did. So this becomes just BI times the natural log of X. That's what that is.
I guess just the idea on the outside.
Yeah, just for emphasis.
Okay.
Yeah. And I wrote it like that. You know, you can take the parentheses away. It's still the same thing, right? I wrote it like that so you can see that this E to the I parentheses beta natural log of X looks like E to some theta times I, where theta becomes beta natural log of X. See, theta is here, right, for cosine theta plus I sine theta. Well, here my theta is beta natural log of X, cosine of theta, which is beta natural log of X, plus I times sine of beta natural log of X. Right? Just trying to match up everything so that it makes sense. So if that be the case, so I go back to this statement here. And so I have y sub c is this x to the alpha times parentheses. And can I do this? I was thinking about this, and I think it'll serve me better. I want to make this c sub 3 and c sub 4. I thought that was pretty cool. C sub 3, C sub 4, C sub 3, C sub 4. And I'm going to do that so that I don't have to do any magic at the end. Typically I do some magic, but I won't have to anymore. So if we call it, so now my answers can be C1 and C2 when I get through. Okay, so this is C sub 3 times this x beta I, but that x beta I becomes cosine, parentheses, cosine beta natural log of x plus I sine beta natural log of x. That's for the c sub 3. Now plus c sub 4, this is parentheses, cosine, well, that's going to be negative up there. So wherever I have the beta natural log of x, I got to write negative because that negative sign is right there. This is cosine, put a parentheses there, negative beta natural log of x plus I sine parentheses negative beta natural log of x. Close this parentheses, close that parentheses, close that bracket. So x to the alpha times brackets. I'm going to simplify this. This is c sub 3 times cosine beta natural log of x plus, say, I c3, I times c sub 3 times sine beta natural log of x plus, here the cosine of a negative terms encompasses that negative. So the translation of that is that it's the same result as the positive. So this becomes here c sub 4 times cosine beta natural log of x. Now the sine of a negative becomes negative times that sign. Look at on the unit circle. So this is minus I c sub 4 times sine beta natural log of x. Close that up. Right. So now what I'm going to do is get the cosines together. Cosine here, cosine there, and then we get the sines together. Okay. Does not like me. Okay, good. So this is x to the alpha. I'm going to get the cosines together. So this is parentheses c sub 3 plus c sub 4 times that cosine beta natural log of x, and plus I'm going to get the signs together. This is I c sub 3 minus I c sub 4 times sine beta natural log of x. Right. So now here's the magic, but it's not as magical as if I would have had C1 and C2. We say let C sub 1 equal to C sub 3 plus C sub 4, and let C sub 2 equal to I C3 minus I C4. This imaginary unit is a constant as well. It's just the square root of -1, right? So then that implies that y sub c becomes x to the alpha times the brackets c sub 1 times cosine of beta natural log of x plus c sub 2 times sine beta natural log of x. Okay. Now if you got just maybe 2 minutes, just work one problem, quick problem there to show you how that is mapped, and then I'm done with this section until after spring break.
We're having our spring break so late because the majority of our friends are having their spring break.
Yeah.
So we've already been having our spring break kind of extended now. We're about to
Yeah, I had, last week my kids had spring break, so I left Thursday after this class. We all went down to Atlanta, so we stayed there until Saturday, and so went to see the Hawks and the Memphis Grizzlies. They played that Thursday night, and so my kids really enjoyed that. And then they had this rap group called Migos, Migos, and they were there. And have you heard their songs? Can you understand what they're saying? No. Have it. You know, I don't know.
Like your whole philosophy is trying to get like the 90s word, like
Oh, for real. I was back in the 80s, man. That was my time. I don't think that's nothing like, man, I remember my group was like Run DMC, Houdini, LL Cool J, back when he was, when he was cool. But anyway, let's go ahead and work. So, again, if it's y double prime, you just simply write m times m minus 1. Plus, if it's y prime, just m. Plus, if it's y, you write nothing. If it's a constant there, you write that constant, right? So it's 4. If it was just 1y, you just write 1. It's equal to 0. So this is m squared minus m plus 4 equal to 0. This is just m squared plus 4 equal to 0. This implies that m is equal to plus or minus 2i. That is a 2. For some reason, the 2's don't come out so well. So m is equal to 0 plus or minus 2i. So alpha is 0 and beta is 2. So y sub c is usually x to the alpha, but x to the 0 is just 1. So all this is just c sub 1 times cosine of 2, that's the beta, times the natural log of x, plus c sub 2 times the sine, parentheses, the beta 2 times the natural log of x. And that's the answer. So getting the answer is pretty easy, but understanding how that answer is of that form, that's always the question. Okay? Yes, sir.
So I'm letting y squared or y double prime equal m times n minus 1, but what do you do with coefficient?
It stays there. If, say, for example, good question, if you had a coefficient in front of this x squared y double prime, if it was 3, you just put the 3 there. It's 3 times m minus 1. The numbers, the coefficients, they have to go, but what's being taken into consideration for the substitution or the shortcut is the x squared y double prime. That becomes the m represented by m times m minus 1. The x times y prime is represented by the m, right? And then here, the y, you remember the y was actually x to the m, but you had factored that out. And 0 divided by that, where you said that x to the m is not equal to 0. So that term went out. So what's left would be the coefficients in these m terms. Yes, sir. Daniel? Yes. X to the third, y triple prime, it still works. The shortcut still works. Yes, sir. M times m minus 1 times m minus 2. Right? Yeah. Okay.